Welcome to Data Science with EJD. In this video, I'll be talking about unsupervised learning projects from raw data to insight. This is more like the last video talking about unsupervised learning. So we'll just do a kind of pipeline to run through a typical unsupervised learning project, and that will end up with a dashboard. Okay, so in introduction and objective, our goal is to uncover hidden patterns in the wine data set. The wine data set is a popular data set for machine learning, projects, and it is used. We want to uncover hidden patterns in the wine data set using unsupervised learning. The data set has 13 features and 178 samples. So that means it has 178 data points and 13 columns or variables, so to speak, like that. So the technology we'll be using, of course, we'll be using Python, scikit-learn, of course, which is popular for machine learning. We'll be using Matplotlib for some visualization, and Plotly Dash for dashboard creation. So the process will involve loading and preprocessing data, reducing dimensions using PCA. You can see the one data set is a 13-dimensional data set because it has 13 features. So we reduce dimensions using PCA. Then we perform K-means clustering. We evaluate cluster quality and visualize results and build an interactive dashboard. So of course, the next thing we want to do is the loading of data. So since we know we're using the wine data set, so import pandas as PD, and then from scikit-learn data set, you import load wine, and then we load the data set. Wine is load wine, and then we create a data frame. X is PD.data frame, wine.data. Since you're focusing on the features, it is an unsupervised learning thing. So we don't need Y, which would make it a supervised learning thing. Like we have a single target, and then all the 12 features, like that. But here we're just focusing on just the features. So if you run this, you can see what the data looks like. Yep. Yeah. So you see it's 178 by 13, 178 rows, 13 columns. That's what that means. And you see the columns are things like alcohol, malic acid, ash, alkalinity of ash, magnesium, total phenols, flavonoids, non-flavonoid phenols, proanthocyanins, color intensity, hue. So these are some wine properties, right? Uh, so that's what this data set is about. So we can do some exploratory data analysis, of course, starting from the time of data analysis with Python. We've done a lot of things talking about exploratory data analysis. So we want to get a statistical overview of these things now. So this tells us, for instance, talking about the color intensity. Of course, we have 178 data points, so nothing is missing. The fact that everything, the count everywhere is 178, so none of this information is missing. And then, if we look at the color intensity now, the average color intensity, as you can see, is 5.05. The standard deviation is 2.31. The minimum is 1.28. The 25 percentile is 3.22. The median is 4.69. The third percentile is 6.20. And the maximum color intensity is 13. You can do that for all the other things, right? So alcohol level, percentage of alcohol, the average is 13. The standard deviation is 0.8. The minimum is 11% of alcohol. The maximum is 14.83% alcohol in the wine data set. So we can also get some info. Of course, we already have an idea so we know we have 178 entries on 13 columns. So the columns now we have alcohol, malic acid, and all of these things, and they're all float variables. So it means you can perform mathematical calculations with all of them. And then the data types, of course, you can see floats, 13 floats. Memory usage is just 13.2 kilobyte, yes. So still visualizing the data, right? We can also do a kind of so we can visualize them. We want to do a heat map to see the correlation between the variables, right? The 13 variables. So if you do this now, we can easily see this. So the reddest parts shows the strong correlations, and the bluest part shows weakest correlation, the most negative correlation, so to speak. So of course, strong on both sides, right? But positive and negative, basically. So for instance, I can see 0.86 jump at me. It tells me that the flavonoids and total phenols are strongly correlated. Now, the essence of something like that would be to, so it means that if you want to do a machine learning a machine learning pipeline, you are good with either of these two. You don't have to use the two. So that's also one way of reducing the variables available. So flavonoids and total phenols are strongly correlated. So you can rest one of them because either of them can give you almost the same result, right? So that's one way to reduce your variables. Then what zero OD280 slash OD315 of diluted wines together with total phenols is also like 0.7. Now you see that's another thing going on here. So you can see how the features, how they relate with themselves. Of course, you don't want to bother about the ones on the diagonal because it doesn't tell us much because it's alcohol with alcohol and all of these things. So you have all that like that. So you want to see let's see the most negatively correlated stuff. Can I see any? I see minus 0.56. That looks like the most negatively correlated. So it means that malic acid and hue have so the higher the malic acid, the lower the hue, or the higher the hue, the lower the malic acid. That's what that tells us. So I mean, this gives us a kind of idea of the interactions, the relationships between pairs of variables in the data set. Okay, so the next thing is we can go for the pre-processing. So since we are doing a machine learning thing, scaling is a very common thing to do here. So you want to check missing values. Of course, in this case, we have seen already from when we did the statistical overview, you can see already that okay, this first one now. So all the counts for all the feature is 178. So it means no data is missing. So if, for instance, the count for proline is 177, that means that one proline value is missing. So it's complete everywhere. But if it's missing, then you can go ahead and delete maybe missing values or impute values there or something like that, depending on whatever rule you want to follow. So data processing, you check missing values. None is expected here, just like I said. Then you can scale features for PCA and clustering. So for scaling purposes now, or clustering, which are also unsupervised learning duties, so you can you can for representation using PCI and clustering, you need to scale the features, right? That's basically what's happening. So from scaling that's preprocessing, import standard scalar. So missing values check. Of course, there's no missing values. So this one check to show missing values. So it will show you all the variables and see if any value is missing. If nothing is missing, it shows you zero all through. For the standard scalar now, so we scale and then the x value now is now scaled. So we have x scale is now scalar dot fit transform of x. So by running this, we transform x. So you see everywhere nothing is missing because we have all the 178 data points given for each variable. Okay, and then you also see that okay, we've done the scaling. Okay, well maybe we also want to maybe let me try to see if we can visualize the scaled value variables now instead of those numbers. So we just have x scaled now. Yeah, x scaled. So the scaling it just talks about normalizing. So for each set of variables now, we have normalized them to have mean 0 and standard deviation 1 like that. Okay, that's x scaled now. Then we go ahead and do dimensionality reduction, which is also an unsupervised learning task with uh PCA, is it power component analysis? Yeah, PCA. I keep forgetting PCA. PCA is power component analysis. Principal component analysis, sorry. Principal component analysis, yeah. So we reduce 13 features to 2 principal components for visualizing and noise reduction. That's like that's imagine reducing 13 dimensions to 2 dimensions. That's one of the beauties of PCA without losing so much of the information. Of course, it all depends on the data and all that, right? So so this is the process for dimensionality reduction using PCA. So from scikit-learn.decomposition, import PCA. So PCA now is PCA, the number of components. We want it in 2 components now. Of course, with Plotly, we can do 3 components. Random state is 42 for reproducibility. So XPCA now is PCA.fit transform X scaled, right? Then so it now becomes a PCA data. Instead of having all the 13, we just have 2 now. Then you can now print explain variance ratio by PC1 and PC2. So it will give us all the ratios. And total variance explained. That'll be summation of the explained ratio for PC1 and PC2 together. Then we visualize using matplotlib. And then, of course, we have all these titles right here. We do a scatter plot of this. So you see, so explained variance ratio by PC1 and PC2, you have 0.3619. So the principal component 1 on the x-axis here explains just 36.2% of the whole data of the data set. And then the principal component 2 on the vertical axis explains 19.2%, something like that. So the total variance explained by this is just 55%. So this PCA, of course, it does some job, but it doesn't do a very reliable job. So if 55% is not accepted, you may have to think of other PCA is a linear method, right? So we can use non-linear method like TSNE, that's T-distributed stochastic neighborhood embedding, or UMAP, right? We can use one of those two. But for now, we have used PCA here. Okay, one thing I wanted to also show the other time was, now that you have scaled using PCA, right, you may also be interested in seeing the XPCA, right? This XPCA that was done right here. You may want to see what that looks like, since we have changed 13 dimensions into 2 dimensions, XPCA. So instead of having the 13 we had before, we just have 2. So you can see it's just 2 side by side now. We have 2 dimensions now. So 13-dimensional stuff. The 13-dimensional thing we had up here, this one out like 1, 2, 3. If you count, it's 13 in all. Now it's reduced to 2, and that's the job of PCA, right? And then we go for clustering with K nearest neighbors, with K-means. So cluster data PCA, cluster data based on PCA components. That's what we're doing now. And of course, anytime we are doing K-means, because of MKL memory leak on Windows, we can we do these first 5 lines, which actually helps to suppress that error message. Then from sklearn.cluster, since we want to do K-means now, we import K-means. So K is 3, this is known from wine dataset classes. So we are doing K equals 3. So K-means now is n clusters, K random state 42 for reproducibility. So clusters now K-means fit predict KPCA. So of the PCA data we already have, we now want to group them into clusters. So you can then append cluster labels for later use now. So you have PC1, PC2, DF cluster is clusters. You are adding that to the DF now, to the data frame. And then we run this, and then K, and we have this now. So you now have 3 clusters. You have the yellow clusters, the something like purple clusters, and some greenish clusters, like is it army green? That is called now, some kind of green thing. So you can see from that now we have these 3 clusters. Okay, the next thing we want to do is to evaluate the clusters. I did a whole video on clustering metrics, right? Like silhouette score, Davis-Baldwin index, and RAND index. Is this some RAND index, ARI, right? So use internal metrics. Of course, ARI is an external metric, so we can use internal metrics. So since no labels are needed, we use external metrics if labels are needed, right? Okay, so from sklearn metrics, we import silhouette score, Kalinske Harabaz score, and Davis-Baldwin score. So for silhouette score, we just have silhouette underscore score, X underscore PCA clusters, Kalinske Harabaz underscore score, X PCA clusters, Davis underscore Baldwin underscore score, X PCA clusters. So we get all of this in 3 decimal places. So for silhouette score, we have 0.56. That's silhouette score should be as close to 1 as possible. Kalinske Harabaz index, as I have a feeling that should be between 0 and infinity. That's why we have it this high. Then Davis-Baldwin index should be close to 1 also, I think. Or Davis-Baldwin index should be between 0 and infinity also. But I mean, silhouette score, we know that so well. This is just 56%. That's not that's a far that's good, but it's a far cry from what we want. It's not as close to one as we might want. So it all depends on what you are willing to accept, though. So, but this is what we have in this case. Then we can then go ahead and do hyperparameter tuning. Since we don't have this the kind of silhouette score we like, we can make it a bit better if possible. So for hyperparameter tuning, where we are choosing optimal value of number of clusters, right? So you can use the elbow method and silhouette scores to choose best K. We saw this under K-means clustering, right? So here now, of course, we need numpy matplotlib.plot. K means silhouette score again. Then we have WCSS. We've talked about this before. Silhouette score K range 2 to 11 for K in range. So we want our K to be between 2 and 11, right? So we can do that. So we now have K means is this. K means dot fit WCC dot append. K means inertia. Silhouette score we append that to. So at the end of the day, we want to get the best of each of these things. Oh, that WCSS is within cluster sum of squares. Exactly. So we run this now. So for the elbow method, so where the thing begins to have an elbow, that tells you the possibility of the number of clusters we should have. So this tells us we should have about three clusters, right? When you come here to for the silhouette score, the silhouette score also seems to correspond with having three clusters, because the peak of the silhouette score for me looks a bit more readable than the elbow method. So this is the silhouette score right here. So it tells us K should be like 3. So now we have something to work with. So when we go to the next place now, so we see K should be 3, right? And 3 was used up there already, so we don't have to worry. 3 was already used for the clustering. Yeah, we already used K here, so there's no big deal. So if that changed, then we could go back and redo that. All right, that's talking about the elbow method and silhouette scores. Then for visualization and interactive dashboard now. So here we try to make the dashboard. Yeah, so import dash. So from dash import DCC and all that. The dashboard core components, HTML, blah blah. So import Plotly Express as PX, that works in Plotly properly. So DF cluster as type string for color mapping, and then we do the whole scatter. So PC1, PC2, K-means cluster of PCA components for wine datasets, and so on and so forth. Then we have unsupervised learning project. So this is like the title for the dashboard. So if you so this line 24 and 25 help us to run the dashboard. So we run this, and then we expect the dashboard to come jumping out. Exactly. So we have it. So unsupervised learning project now. Oh, okay, I've affected that. So, Plotly is interactive. So if you touch it, you can change something. So if I, touch it like this, I can spread things out. I can bring it back together or something. But if you are lost about what you have done, so just go back and run it again. So, oh, okay, I've touched it again. Okay, run again. And be careful this time around. Okay, good. So now we have the clustering looking this beautiful plotly. So we have 3 clusters, 0 cluster red, first cluster 1 green, cluster 2 is like purple, so for the wine data set. So the silhouette score is 0.56. The Kalinsky Harabas index is 343.949, like we saw before. So that's the dashboard. Of course, you can do more things if you want, pie chart, bar chart, and whatever. You can do that. If you want to know more about bar chart, like dashboards, you can check my the playlist on data analysis with Python. I did quite a number of dashboards. They're using Plotly and Bokeh, right? So summary and next steps now. So we loaded and explored the wine data set. We scaled features and reduced dimensions with PCA. We clustered using K-means and evaluated clustering performance. We used elbow and silhouette methods to confirm the number of clusters, and we built an interactive dashboard for exploratory visualization. Next steps could include how you can improve this, right? So since you looked at the PCA, you discover that the silhouette score, for instance, is 0.56. If you want something better, you may check out the TSNE, other dimensionality reduction algorithms like TSNE or UMAP for nonlinear dimension reduction. You can also add cluster interpretation by analyzing feature distributions per cluster. You can apply clustering on original scaled features for comparison, and you can export dashboard or results to share with stakeholders. So that's like a mini project that we've been able to do based on our knowledge of unsupervised learning. Of course, the project could have been about of course, we put clustering together with dimensionality reduction. Then the other thing will be associative learning rule, right? So we come to the end of this video with this. Let me know how helpful this is for you, and if there's something you'd like me to do, there's something you'd like me to try, feel very free to let me know. If you have subscribed already, thank you so much for that. I think we need about 3 subscribers to get to 1,000 finally. So you can make that happen. Go ahead, subscribe. And of course, 1,000 is not the final destination. Right? I can't wait to get to 100,000 too and get that plaque, and get to 1 million one day. So I know it's very possible. So you can make that possible. Just go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. And of course, you can go an extra mile by becoming a member of the channel for some extra privileges. So just click on join and you see those possibilities and the perks attached. By the way, I have my data sheets and my code sheets and data sets. They are all available. If you just look at the description box, you find a link to a Google Drive and you can download all the files. And that's true for data analysis with Python, SQL with Python, and of course, data science with EJD, this one now. So after this video, I think I can maybe go for reinforcement learning, deep learning, or natural language processing. So let's see which one that will come after now. So, of course, you want to stay glued to this channel and share and like so that more people can have access to the great content we have going on here. Till I come your way again, keep doing data right. Bye.